Okay, so welcome back, and today I want to spend some time talking about rational functions and a graphing strategy for rational functions. So you can see I've given you here a lovely function, and I've even put it in the graphing calculator, but that should be, note to self, this little snapshot here, that should be a last resort. Putting it in your graphing calculator should be a last resort. So I'm going to talk about how to get all of these things analytically. So here's our strategy. Let's try and find the y-intercept first by hand. You know the recipe. Let x equal 0. Okay? So if I let x equal 0 here, 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 and here, you can quickly see that f of 0 is basically going to end up being negative 8 over negative 12, which is 8/12. And let's see, 4 goes into 8 twice, and 4 goes into 12 3 times, so 2/3. So 2/3 is where the y, so basically 0 comma 2/3 is where the y-intercept should occur. And we can verify that. I mean, we can see that right there on the graph. Okay? Now the vertical asymptotes. Now, by the way, on your graphing calculator, when you see those straight vertical lines, those are the VA. They're actually, I like to make them dashed. So this should be like a dashed line here and a dashed line right here. So it's appearing just visually that there's going to be a vertical asymptote at 4 and at negative 3. But let's see what happens with the algebra. So to find the vertical asymptotes, if you're looking for a recipe, you take the bottom, the denominator, and you set the denominator equal to 0 and solve. All right, so if we do that, we'll have x squared minus x minus 12 equals 0. Hope that it factors. If it doesn't factor, you might have to use quadratic formula or something like that. Plus and minus, x and x, and then 12 factors with 4 and 3. So we'll put the 4 here and the 3 here. So clearly there's two values of x, namely 4 and negative 3, that cause that to be 0. So I'm going to temporarily erase this part here. So now we know that the vertical asymptotes occur here at what x values solve this. So occur at x equals negative 3 and 4. And that matches very nicely with our graph, as we see here. Now let's target the horizontal asymptote. I'm sure from your reading and being in class and listening to other podcasts, by now you know that for the horizontal asymptote, if the degree of the numerator, I abbreviated here, numerator, is equal to the degree of the denominator, you just take the ratio of the leading coefficients to be your horizontal asymptote. So you can see here, the degree 2, degree 2. The degree of the top is the same as the degree of the bottom. Therefore, the lead coefficient here 2, lead coefficient here 1. So y equals 2 over 1, or y equals 2. So therefore, we know there's going to be a horizontal asymptote at y equals 2, the ratio of the lead coefficients. Now, if we go back to the graph, you see, oh yeah, the function does approach 2 and never cross it. See? Approaching some y value and never crossing it. And you can see that that y value that it's approaching, is right at 2. So let you explore. It's nice to have the technology and the apps and the graphing calculators to help us explore that, what we're finding to be true analytically. And last but not least is the x-intercept. So now we target the x-intercepts. And the recipe for that is to let y equal 0. So if I let y equal 0, and I just show you, if I let this equal 0, then it becomes pretty straightforward to solve. You'd have 2x squared minus 3x minus 8 all over x squared minus x minus 12, equals 0. But when you cross multiply that, I mean, anything times 0 is 0. So you really end up interested in where does 0 equal the numerator here. 2x squared minus 3x minus 8. Now, if you luck out, that factors, but I would just identify that A is 2, B is negative 3, and C is negative 8. And I would just start plugging and chugging into quadratic formula. So I'll hit pause as we do that. So by now, I'm sure you're comfortable, negative b plus or minus the square root of b squared minus 4ac all over 2a. So I've laid that out for us here. If we crunch that out, we should arrive at 2 decimals locations, and those decimals should match up with what we get. I'll hit pause as you sort of get the decimals on that. So I'm sure you've typed this out by now and arrived at the very same decimals that I've arrived at here. So 2.88 for one of the x-intercepts and negative 1.39. And what I did is I went back and looked at the original graph and say, does it look right? So yeah, it looks like it hits right there at the 2.88. And the other one does look like it hits right there at the appropriate decimal. So now we've found our x-intercepts, we've found our y-intercept. All of those things would lead you into creating the correct sketch. And just to let you know that, if you did do it by hand, you would sketch in your vertical asymptotes, which occurred at negative 3 and 4. So you'd always sketch in your vertical asymptote here at negative 3, 1 at 4. You'd sketch in your horizontal asymptote, and I'm just thinking about, how you would do this if you didn't have a graphing calculator. Your horizontal asymptote, we said, was at y equals 2, so you'd sketch that in at 2. And then you just think about where your function resides, and your x-intercepts and your y-intercepts will help you figure that out. So now we know, oops, that piece got a little skewed there. Now we know that it kind of crosses like this and goes down, and that it lives in here, and that it also lives in here. So, a lot of people ask me, if you know the y-intercept is here and there's an x-intercept here and another x-intercept here, you kind of have the flow of this piece, but how do you know where these other pieces live? And that's good old-fashioned, creating an xy table. That's what I meant by free points. You would pick points to the left of negative 3 and pick points to the right of 4, say 5, and literally create an xy table to fill in the blanks. But I just wanted to give you the strategy behind that. Okay, good luck out there.